So we are discussing a way to represent my error term in my logistic regression type problems. And what we saw in the previous video was we came up with this logistic regression error, which wasn't mathematically convenient because it wasn't convenient to minimize it, because that is what our goal is, right? And so also the interpretation of h of x as a probability did not really come out as much. And so what we're looking at is what is a better error function? Like, what is a better way of representing this error function? This is the question that we'll try to answer. What is a better error function for logistic regression, of course, right? And a better, I would say, error function is something that's known as the cross entropy error. And we'll see how we get to this. So this is cross entropy error, and it looks something like this. Okay, so this is obviously averaged over all the data that we have from 1 up to n, and well, it has a slightly complex looking form, but I would say we shouldn't get too overwhelmed by what it looks like, because it looks complex, obviously, with the log and the exponent and all that, but its behavior is better than the one that we had before. And it also has, so it has a better behavior, better behaved, I would say. And plus, it has a probabilistic, which was more important to us, right? So it has a probabilistic interpretation. And obviously, we are going to derive it. Okay, so let us begin. And what we begin with is the data itself. So let's begin with the data itself. And if you remember, this is how my data looks like: x1 input, and then y1, and then we are actually observing these y's, right? So x2, y2, and so on up to xn, yn, and where any of these y's, which I'm denoting by the small n, they belong to either -1 or +1. Okay, so because this is what we observe. We don't observe probability, we observe this YFNs, which are like yes or no type things, right? And then the big, like the important assumption underlying this collection of data is that my data is IID, which is independent and identically distributed. And why do you think that is? Of course, that is because it is one of the important pillars of all the theory that we develop, right? So we assume that this is independent, identically distributed. Now, what is the probability of observing? So we are interested in what is the probability of observing these y's, like y1, y2, and so on up to yn, given that they have occurred or they're occurring on x1, x2, and so on up to xn. What is that probability? Now that probability is nothing but something that we call likelihood, and the way we represent it is something like this. So y1, the probability of y2 observing all of these up to yn, given that they are occurring on x1, x2, and so on, xn. This particular term, first of all, is like, this is basically the probability of obtaining my data. It is the probability that the data that we have, the data that we are observing, for example, the outcomes of the data that we are observing, they are based on the fact that we are observing this, like we are observing these y's because x1, x2, xn are there, and this outcome is occurring because of these x1, x2, xn, and so on. Okay, so this is known as likelihood. And okay, so now because we said my data is independent and identically distributed, this can be written as these probabilities can be also written as y1 given x1, right, from the fundamental law of probability the law of independence, right? So this is y2 given x2, so on up to probability of yn given xn, right? Which in turn can be written in a more like compact form, which is the overall product from n equals 1 up to n p y of n given x of n, right? So this is how in like a very compact form we can write this like this probability of observing my y's essentially, right? So now this is the probability that the data were generated if my f, like my target function, was actually h, right? Because h is something that I can calculate and f is something that's unknown, right? So in other words, this term is actually signifying or representing my h x of n if my y of n is a plus 1, or this could be 1 minus h x n if my y of n is minus 1. Okay, so what does this tell us? What does this tell us about the initial definition of my h of x of n that we had? What does this tell us about it? Well, we know, like this was known earlier, and we know that h of xn, because we are like using this sigmoid function, is w transpose x of n, right? And so we also know that 1 minus h x n would be 1 minus theta of w transpose xn, right? And if you remember the properties of the sigmoid, we can also write it as the theta of minus w transpose x of n, right? Because, let me quickly remind you, minus s is 1 minus theta of s because of this small property here, right? So if, like, I can summarize this part again here, right? So if, let us say my yn, what I'm observing, right, is a plus 1, right, of one of the categories, right? Then my h of x of n, because this is how I summarized it, my h of x of n can be replaced by this because this is the data I have. So essentially I'm going to like rely on that, right? So my if y of n equals plus 1, then my h of I would say x of n can be replaced by this, like theta of w transpose x of n, right? And similarly, if my y of n, if what I observe is minus 1, then my h of x of n can be replaced by theta of minus w transpose xn. Why? Because I know this from this small box here, right? So if we summarize these 2 points now, put them together in a more concise form, right? Basically, what I'm saying is I can put these 2 points together in some ways and write this function as like more of a single representation of both of them by saying this is theta of yn times w transpose x of n, right? So what do we get? Like once we have arrived at this final definition of this conditional, the product of all the probabilities up there, what do we arrive at? Well, we arrive at something that is telling us that this n is from 1 up to n p yn given xn implies or is equal to the theta of, like this thing. I'm not writing the entire thing, I'm going to write it like in another line, but this thing, this only this p part, right, this like signifies, or this represents yn w transpose xn, right? So then, like more formally, what we are saying is we have this likelihood function, which is most of the times represented by L, and then L, or the likelihood function, is given by n equals 1 to n theta yn w transpose xn. Okay, so this is my likelihood. So just to kind of remind you, this is like if your h is fairly close or it approximates your f really well, then the probability of obtaining this data, whatever data you have, like the x's and the y's, must be very high. This is what this is like. This is what this means, right? The meaning of this is that as I said, if your H approximates F really well, then the probability of obtaining that data must have been very high. And if it does not approximate to F, then the probability of obtaining your data or observing the data is not as high, right? So this is what likelihood function represents. This is what this is representing. Now, what is our goal going forward? Well, our goal is to choose the weights W here, right? So what do we need to do? What is our goal? Well, choose your W's, right? Weights such that you can maximize this probability to observe the data, right? I mean, I have to maximize this, choose W such that this we have to, like, our goal is to maximize the probability of observing this data, because if I have a higher probability of obtaining that data, then I'm really close to my original underlying target function, right? So I have to choose W such that they maximize this function, this likelihood function. And this is a very well known technique in statistics and also now in machine learning, that's known as the maximum likelihood, also known as the maximum likelihood estimation, or sometimes known as MLE. So maximum likelihood estimation, and this is a very well-known technique, as we said. So we want to maximize my L, right? This is the thing that I want to maximize. Now, of course, like there are certain known techniques of how to do that, right? And there are certain because this is like, of course, a function, and then there's a product of everything, and so we'll have to kind of come up with a more concise sort of expression, and then minimize or maximize that, right? Whatever we want to do. So we'll be using some facts from mathematics, and then we're going to apply to our function or the likelihood that we have. Okay, so some facts from mathematics. If there is a function, let's say L of W, and now I'm like adding to this L that this is a function of W, because weights are the things that we will be like finding, right? So we have to maximize this with respect to my X, with respect to my data. And so what I'll be doing, so first of all, maximize this function, right? And there are certain known facts about when we are maximizing our function. So let's say I'm finding max, instead I'm writing R max to be technically more specific. And so this is equivalent, like if I'm saying R max of L of W over W, this is equivalent to saying that I'm trying to find the arg max of the log of this function. These are mathematical facts, I'm not making them up, right? And so this thing further is also equivalent to saying that I'm trying to find the arg max, of course, W and 1 over n log of L of W, and which in turn is equivalent to saying that this is equal to like finding the arg min of the negative of 1 over n log of LW. Okay, so we are, again, to be mathematically more convenient, we choose this out of all the equivalents of whatever maximize, like basically we started with this, and then we said that these are all the equivalents of this, and we eventually come up with this function. We don't come up with this function, or obviously this is also one of the equivalent ways of expressing the argmax of L of W. And so we are going to choose, so like mathematically we're going to do this. So basically what we're trying to do is we are going to choose weights W's to minimize, because we have a negative here now, right? So instead of maximizing, I'm going to minimize this minus 1 over n log of L. Basically, both will produce the same thing, whether you maximize or you minimize, but it has been found theoretically that this one is easier to achieve. This is easier to it is easier to ascertain certain properties of this function, and so that's why we pick this, right? And so basically we are trying to find the min of, and let me write it down. So therefore we are interested in finding the min of minus 1 over n summation to n log of theta y n w transpose xn. This was the original that we came up with, right? And so we're trying to minimize this, and because remember this was also a mathematically very convenient function, the sigmoid function, and so we can rearrange, I would say, rearrange the terms and then come up with log 1, because the negative sign goes in, and remember this is a sigmoid yn w transpose xn, right? Which further can be simplified to something that looks like this: 1 over n, I is from 1 up to n, log of 1 plus e minus yn w transpose xn. Okay, so this here is my cross entropy error, which we talked about earlier, right? So what we have to do is to choose weights W that minimize this in-sample error. So this in turn can be written as E in over W, right? So this is the final cross entropy error that we are going to essentially minimize. And obviously to minimize that, now we know that this is the expression that we need for E of n, but to minimize that we need a process, right? So we need an algorithm. We're going to talk about that algorithm in the next video.